Here ends our unit on simple harmonic motion, aka things that look really nice in a differential equation, but only bear the smallest resemblance to what you see in the real world. Let's start on complicated harmonic motion, aka what the real world is actually like. Is this going to be on the AP? No, it's not going to be on the AP. It's just going to be at that big university we call real life. Let's talk about damping. Here's a spring. It's on the tabletop. We're looking at it from above, so there's no pesky mg. You take it, you pull the mass this way as hard as you can. You'll feel a restoring force of kx going the other way. Then, once you're at your maximum displacement, you'll let go, you'll let fly, and you'll also find a drag force going the other way. Let's say, for the sake of the argument, that this is in air, so your drag force isn't tabletop solid surface friction, and let's say of the two models of drag force with which we're most familiar, it happens that this particular shape is associated with the easier one, BV. So you've got two restoring forces. One is the Hooke's law, and the other one, which is the drag force, which opposes your motion in any direction. Check your vectors, make sure everything is in the same direction. That'll give you your net force, and that'll give you your acceleration. So write that down as a differential equation. Get as far as you can. This is where the test question says, write but do not solve the differential equation. Press play when you're ready. Because if we're writing everything in terms of x, that is going to be a nasty differential equation. This we could solve by itself, no trouble. This we could solve by itself, no trouble. The issue is both of them together. The solutions to both of them, the ones we expect, are harmonic motion for the second order differential equation with an angular frequency of the square root of whatever's out front, aka k over m, and a maximum amplitude of whatever your maximum displacement does. For the first order differential equation, we're expecting exponential decay at a rate of b over m. Well, we were close. Turns out in this case, in the more complicated differential equation, it turns out the solution comes at a rate of b over 2m. Advanced math students who know how to solve a differential equation like this are strongly encouraged to fire up those thrusters and give it a try. When the dust settles, you'll see the leading coefficient, a for amplitude, as ever was. You'll see that cosine function that you were expecting with an angular frequency and whatever phase shift is appropriate to the problem, and you'll see damped harmonic motion. Not just a regular cosine, but a cosine that dies down over time, getting smaller and smaller until it trails off completely. The interesting part here is the angular frequency. It's not k over m. I'll grant you it starts at k over m, and if you've got a damping factor of b equals 0, aka no damping, or b is practically 0, negligible damping, you'll get k over m. But if there's non-negligible damping, this is the angular frequency we're going to get. And we're going to get so tired of calling that k over m, too many syllables, we're going to call it omega naught. We're going to call the square root of k over m omega naught, so that these two terms match up. And this omega naught is our definition of the system's natural frequency. When we talked about resonance last year, we said natural frequency is the frequency at which the system is best suited to vibrate. And in this case, this system is best suited to vibrate with an angular frequency of rad k over m, exactly the way the mathematics predicts from the differential equation, without overmuch concern for what's going to happen in the real world. Pretty cool, huh? You can see why we're doing damping and resonance in the same unit. Now, if you haven't done your online lab yet, press pause and try it first before taking notes on the solutions. You can see from what's under the square root in the angular frequency termed above for the damped harmonic system that there are going to be three cases here. One of them is the big positive and obvious ones, where k over 2m is greater than b over 2m. This is where the harmonic motion is going to be significantly more powerful than the damping. This is repeated oscillation. The This is underdamped motion. Damped motion here. It's the graph you usually associated with damped harmonic motion. You can see the harmonic motion and you can see the damping factor exponentially squishing down that amplitude. Case is the one where the square root of k over m equals the square root of b over 2m. This gives us an omega of 0. That means the leading coefficient of the t in this harmonic motion equation is 0. That means there isn't a cosine, and the only thing that's left is a factor. This describes two cases. The first case is the case of overdamped motion. Overdamped motion looks like exponential decay. The damping has completely taken over. The function dies down slowly, and if you're lucky, it eventually gets to 0, or something a little bit close enough to 0 for government work. Critically damped motion is the perfect case where you return to equilibrium without oscillating. Critically damped motion is what engineers try to set up when they don't want the system to oscillate, but it's spring-loaded and they have to deal with the possibility. Critically damped simple harmonic motion at omega equals b over 2m is going to look closer to this. Check out the full solution models with the calculus at mathworld.wolfram.com. There is, of course, one more possibility that we have to take into account, and that is that you need to check your math. If omega naught is less than b over 2m, you're going to get a complex solution. It's going to be as imaginary as Bacon Airlines, and you're not going to get any oscillation. Look over your 3 door examples for the different constants that you played with and see which ones are underdamped, which ones are overdamped, which ones are critically damped. Then, when you're ready, go on to the next video where we add a pumping force and talk about resonance.